Okay, my dear students, so today we are going to start with the next part of the transition elements. Okay, so let's start with it. So today we are going to start with the color of complexes. How the different complexes show the different color. So color of complexes. Look at it. Copper. These are color. So how different color complexes they are formed in the nature. So we are going to discuss them. Okay. Let me give you one example. Let's suppose if the copper, if the water ligand is attached, it is having the blue color. If the ammonia is attached, it would be deep blue. And if the chloride is attached, that is yellow solution. So why? The transition element is same. By attaching the different ligands, the colors they would change. So what is the reason behind it? We are going to discuss those reasons. Okay. So before starting this one, my dear, let me tell you first of all, we got the D subshell. Okay. You know that D subshell it got five orbitals. Five orbitals. Okay. So D subshell it got five orbitals in it. Out of these five orbitals, the three D orbitals are present in between the axis. Okay. So the three d orbitals they are present in between the axis, whereas the two d orbitals are present on the axis. Okay. So you got the three d orbitals which are present in between the axis, and you got two d orbitals which are present on the axis. So the two d orbitals which are present in between the axis, their names are dxy, dyz, and dzx. Okay. Whereas the two d orbitals which are present on the axis, their names are dx square minus y square, and the second one that is dz square. Okay. So these are the different orbitals. Okay. So let me tell you one more time. D subshell got five orbitals. Out of these five orbitals, the three d orbitals they are present on the axis. Okay, and they are dxy, dyz, and dzx. Whereas the two d orbitals they are present in between the axis. Okay, they are present on the axis. Okay, they are dx square minus y square and dz square. Okay, so let me draw these orbitals for you. Have a look up here. Whenever you want to draw any orbital, so you should draw the axis first of all. Okay, so draw the axis three times. Okay, okay, this is x-axis, this is y-axis, and this is z-axis. This is x-axis, y-axis, z-axis. This is x-axis, y-axis, and z-axis. Okay? It's in there. Yeah, yeah. In uh, just like that, we want to draw the two orbitals up here. So first of all, draw the axis. Okay, this is x, y, z. So this is x, y, and z. Okay. Now just look up here. The three d orbitals they are present in between the axis. It means These are the axes x, y, z. So they are present in between these spaces. These spaces. Okay, these spaces, these spaces. So they are present in between the axes. When I say the d orbitals, they are present on the axis. On the axis means they are present on axis like that. On the axis. Okay, this means that. Let's suppose the first one that is dxy. So dxy. So where all the axes they meet, we got a nucleus up there. Okay, the first one is xy. So it is present in between. This is x, this is y. So it is present in between x and y like that. This is y, this is x. Okay, it's one eight is present like that. The other eight looks like present on the z-axis, but z-axis is coming out of the page and into the page. This eight is not present on the z-axis. Z-axis, if I draw it three-dimensionally, it is present in between x and y, like that. Z-axis is actually coming into and out of the page. Are you getting it? Yeah. Muskan, yeah, yeah. Did you get the point, beta?
Yes, sir.
Yes.
Okay. The second one that is BYZ. So here the nucleus is present, so it is present in between the Y and Z, like that. Okay, Y and Z. So this is Y and Z. So if I draw, so now this time this x-axis, what's up? This x-axis is moving into and out of the page this time. This is not present on x-axis. This is actually right behind it, y or z इनके दरमियान मौजूद है. Okay, this is not present on x-axis. X-axis is this time coming into and out of the page. Okay, the next one that is dz. Okay, so zx. So this is z, this is x. Now this 8 is not this 8 is not present on the y-axis. Right behind it, this is present in between z and x. Okay, so if you see the three-dimensional pictures on the Google, you can see that they are present in between the axis. Okay. Now, if you look these orbitals, my dear, dx square minus y square. Okay, so its one eight is present along the x-axis, and its second eight that is present along the z-axis, like that. Okay, so this is dx square minus y square, and then we got dz square. So dz square is this one. Okay, the other eight is present right behind it. And this is, I'm going to draw the 180-degree angle. So this is 180-degree angle, and the same thing is present right behind it. Okay, let's take an example. Let's suppose if this is the blue marker, this black marker is present right behind it. आपको black marker किसी को नजर आ रहा है? नहीं आ रहा. तो वो exactly it is present right behind it. Just name shape. Yeah. The rest में भी होता है in and out का. Then is coming now because they are present on the axis. Okay, so now what the thing we have done yet, the d shell has got 5 orbitals. Out of these 5 orbitals, the 3 d orbitals they are present in between the axis, and they are dxy, dy, dzx, whereas the 2 d orbitals they are present on the axis, that is dx square minus y square and dz square. Okay. Can I wrap this one, guys? Okay, my dear students, now everybody just focus up here because this concept is a little bit easy and difficult. If you get it, it would be easy. If you do not get it, then it would be a little bit difficult. Okay. Now, as soon as have a look up here, the transition metal, it has got the 5 d orbitals. And these five d orbitals, they are present on the same energy level as soon as a transition metal has not made any complex. But as the ligand approaches to it, okay, for making the complex. So what would happen? The ligand provides its electron either through the axis or in between the axis. Okay. In case of octahedral complex, octahedral complex. What are the octahedral complex? Octahedral complex are those complexes in which six dative bonds are present. Six dative bonds. Okay. So in case of octahedral complexes, the ligands, they provide their electron through the axis, through the x-axis, through the y-axis, and through the z-axis. Okay, and you know that the two d orbitals, they are present on the axis, so they also got the electron. So electrons are coming through the axis, and they also got electrons. So electron and electron, they would repel each other. So they are having the forces of repulsion. So whenever there are present the forces of repulsion, the energy level that would increase. Okay. Those d orbitals which are present in between the axis, okay, they are also having the electron, and electrons are coming through the axis. So in between the axis orbitals, their electron and the electron coming from the ligand, they would also repel each other, but their force of repulsion is less. Okay. Let's suppose if this electron is present in my way, but sir, just come up here. Take this pen up here. Okay. Let's suppose these are the two orbitals. These are present in between the axis. This is on the axis. Now ligand provides its electron through the axis. Through the axis. Okay. So now when it approaches to it, so this is very close to this one. This is little bit away from it. This one is away from it. So it means the ligand provides electron through the axis. So the two d orbitals which are present on the axis, they experience greater repulsion. Okay. So what would happen? They would shift slightly at high energy level. So this d orbital split up into two sets. The two d orbitals which experience greater repulsion, they will shift slightly at high energy level. The three d orbitals which are present in between the axes, they also experience the repulsion, but that repulsion is less. So they would remain at low energy levels like that. Okay, like that. So your d orbital, that would split into two sets, two at the high energy level and three at low energy level. Okay. So whenever you want to fill the electrons in them, if you fill the electron in this one, what you do? You put one electron first, okay, and then pair it up. But up here, when you fill the electron, you should fill one electron up here, then pair it up, and then move towards up here. Then put electron up here. Did you get it? Because these are the two different energy levels. This is at low energy level. This is at high energy level now. Okay. This happens for the octahedral complex. But in case of tetrahedral complex, tetrahedral complex, tetrahedral complex in which four dative bonds are formed. Four dative bonds. Okay. So in case of tetrahedral complex, the ligand provides its electron in between the axis. So in between the axis, you know that there are three d orbitals. Okay, dxy, dyz, and dzx. Now they experience greater repulsion. Why? Because now the electrons are coming in between the axis. So those orbitals which are present in between the axis, they will experience greater repulsion. So they would shift slightly at high energy level. The three d orbitals, they would shift at high energy level. The two would remain at low energy level. In case of tetrahedral complex, okay, Is it clear, my dear? Now listen to me again. Firstly, when the transition elements, they have not formed any complex, okay, so all the d orbitals, they are present at the same energy level, the first thing. But as soon as a ligand approaches to the transition metal ion for making the complex, it provides its electron either through the axis. So if it provides electron through the axis, the two d orbitals, they are present on the axis, so they would shift slightly at high energy level. The three, they would remain at low energy level. Okay, and when you got the tetrahedral complex, in the tetrahedral complex, you got the four ligands, four dative bonds are formed. So the ligand provides its electron in between the axis. So in between the axis, you people got three orbitals. So three orbitals experience greater repulsion. So they shift at high energy level and two would remain at low energy level. Now, if you want to fill the electron up here, first of all, we should fill one electron up here, pair it up, and then put the electron up here. Okay? So d orbital has been separated up. Now, the difference of the energy level between the two sets of d orbital, that is delta E, and that delta E, it depends on the type of ligand. If let's suppose it would be water, the distance delta E value would be different. If it could be chloride, delta E value would be different. If it could be ammonia, the delta E value would be different. And this delta E, it comes in the range of visible light. Visible light. Visible light, you know that it is actually white in color and it got salmon colors. There, Goyle. Okay, so this difference of energy level that comes in the range of visible light. Visible light is able to cause d-d transition. D-d transition means that jumping of electron from low energy to high energy level. Let's suppose if energy is absorbed, this electron would jump from here to here, okay, and then after some time come back up here. Okay, so this is called as the jumping of electron from low energy to high energy level. Okay, this thing happens in the ordinary elements as well, but in those elements, visible light is not absorbed. Invisible light like infrared, UV rays, microwave, all these radiations, they are absorbed. We are unable to see them. If they are absorbed, doesn't matter. We are unable to see it. Okay, so this process of jumping of electron from low energy to high energy level by using the energy from the source, okay, that do happen in every element. But in case of in case of transition element, the difference of energy level comes in the range of visible light. So visible light is able to cause d-d transition, jumping of electron from low energy to high energy d orbital. Okay, and due to absorbance of visible light, different colored complexes are formed. Let's suppose if it is ammonia, all these part of the light that is absorbed. So the thing which is absorbed, it would finish. The thing which is not absorbed, green is not absorbed, so that complex would be of green color. Simple as that. Let's suppose if you got this thing, okay. So these all things, they are absorbed. They would finish. Red is not absorbed, so the complex that would be of red color. Okay, let's suppose the color of my let's suppose the color of the marker. If you see, that is blue. So why it is blue? White light is coming to it. Okay, all the colors of the white light are absorbed by this slate. Only blue is not absorbed. That blue comes into my eyes. That is why it looks blue. Okay, so you see different colors in the nature. That is due to the reason that all the white light colors, they are absorbed in that particular thing. Okay, and the color which is visible, that is not absorbed, that enters in your eyes. That is why that thing looks that color. Yeah. जी, जो कलर ब्लाइंड होते हैं फिर उनके लिए एब्जॉर्प्शन डिफरेंट हो जाता है, वही तो बता रहा हूँ ना. हर एक चीज की, वही तो बता रहा कि जो कलर एब्जॉर्ब हो जाएगा वो खत्म, जो नहीं होगा वो रिफ्लेक्ट होगा। किसी भी चीज में भाई, दुनिया की हर चीज में ये अप्लाई होगा।